Okay, sorry about the cut there. Last time we were discussing how to refine the order between, among these three hydrogens right here, and I have the conjugate base of them drawn out here. So let's start refining. Okay, again, let's sort them out with the resonance effect, since the atom effect is kind of not useful in this case as they're all on carbon atoms. Okay, so which one does not have any resonance structure? Which one is not able to do any resonance? That will be number 6. Again, lone pairs that are on sp2 hybridized carbon cannot do any resonance. Okay, so this one does not have any resonance, and these two are able to do resonance. These are on sp3 hybridized carbon, and they're able to resonate with the pi electron system that's next to them. So we can start refining our order again. So we have, because 6 is the least stable base, there's not really any tendency of the acid wanting to go to this base because it is so unstable. So it doesn't want to be an acid. So it is the least acidic. Okay, so 6 will be our very first number in our increasing acidity order. And then we have 4 and 7 indistinguishable from each other for now. Okay, that's starting to get a little bit cramped. Let me move away from it later. Okay, right. Okay, so now let's start to look at 7 and 4. So 7 can resonate into this ring to its left and around it, just like this. Again, same path. Okay, you resonate up, and then you push the lone pairs down, push this pi electron up as a lone pair, and push it down again, and push this last pi electrons up. Okay, but this one, because it is in between two aromatic rings, it can resonate not only with the ring to its left, it can also resonate with the ring to its right. So that just doubles the resonance structure that it can have. Okay, so that's already an added bonus to its stabilization. So now we can refine our ranking between these two, okay, to the final ranking of 7, 4, 5, 3, 2, and 1 is our most acidic. So 6 is our least acidic hydrogen, and 1 is our most acidic hydrogen. Do you understand now how to apply ARIO to order different molecules, like a set of molecules, or to order different molecules and hydrogens within the same molecule? Okay, so now ignore all these now, it's a mess, and let's move on to the third problem. So this is based off of the same molecule as this, but now I've methylated all of the hetero atoms. So after a series of methylation, which is adding methyl groups to it, CH3 groups, which hydrogen is the most acidic now. So no more hydrogens on the sulfur, no more hydrogens on the oxygen. So now if you take a closer look, all of the hydrogens that are available in this molecule after methylation are on carbon atoms. Okay, they're all on carbon atoms. So we imagine that we pull off each of the hydrogens one by one and get their conjugate base. That way the negative charges will all be on carbon atoms. So atom effect doesn't really help us here, so we can move down to resonance effect. Okay, so resonance effect, you would look for the ones that have the most resonance stabilization. Okay, all right, so this hydrogen is the same as this hydrogen right here, right? And we say that it can only resonate into and around this ring to its left. Okay, and this hydrogen is the same as this hydrogen right here. Okay, and it can resonate between these two rings. Okay, it can resonate into the ring to its left, and it can also resonate into the ring to its right. So that's doubling the resonance structure. So that's even more stable. But then we have this hydrogen right here, right? That could resonate into and around the ring to its bottom, but it can resonate up to even more electronegative atom. Remember before when we were discussing the resonance structure for this, the reason why this is more stable than this one, because, well, there's like, the reason is twofold. First of all, this has more resonance structure than this one, and second of all, at the end it was able to resonate as negative charge up to an even more electronegative oxygen atom. That would make it more stable, even more stable. So here we have the same scenario. Not only it can resonate into the ring below it, but it is able to resonate up to 2 electronegative oxygen. Can you see? So if we pull this off, we have this negative charge here, and then you can resonate up here. That's one. And then I am gonna use a different color. I'll use red. And then this is also a second path for it to go up. So 2 oxygen atoms would hold the negative charge at the end. I mean, separately, not at the same time. But yes, the negative charge is able to resonate up to 2 potential electronegative oxygen atom. That makes the base even more stable. Okay, so I would say that this hydrogen that was here a few minutes ago before I cross it out, is the most acidic compared to this and this. Okay, now these cannot be choices because they would be lone pairs on sp2 hybridized carbons, and there's no way to do resonance with them. This one, okay, so I heard there have been some misconception of pulling hydrogens next to like electronegative atoms such as oxygen or sulfur. Now these hydrogens are not acidic at all. In fact, they might even be more than 50 pKa, and that is really not acidic at all. This is the reason why if you pull it off, you have your lone pairs there, right? But then the oxygen or sulfur next to it also have its lone pairs in them. Okay, I'm just gonna draw. The lobes may not be correct, but there are clouds of electrons on the oxygen atoms, and electrons being these close together, they hate each other. Okay, like charges want to repel from each other, so they want to get away from each other as soon as possible, as far away as possible. So they hate this. Okay, so do not pull hydrogen off of carbon next to oxygen or sulfur. Okay, so these are not an option. Absolutely not an option. Okay, so yeah, so this hydrogen that was once here before I cross it off would be the most acidic. Okay, so we're done with these 3 problems. Right, so let's move on to the next problem. Okay, so for this next problem, I have hydrogen A and hydrogen B sticking off the methyl group there. Which one is more acidic? And I highly encourage you guys to use drawings as part of your explanation, because you're gonna have to. It's, I would say, more efficient than writing a paragraph. Okay, so which one is more acidic? So how to evaluate acidity is to again assess the stability of their corresponding conjugate base. Okay, so here at the top I drew their conjugate base. So this is from pulling off HA, and this second one is from pulling off of HB. Okay, so let's apply ARIO, because we are looking at the bases now. Okay, so we can apply ARIO. Again, atom effect, because the negative charge is on carbon atoms, the atom effect does not really help us that much. So let's move on to resonance effect. Now here, in both cases, they're able to resonate the negative charge away from the carbon atoms. So let's evaluate which one has the best resonance structures, or if they have the same resonance structures. Okay, so let's start by looking at the conjugate base of HB. Let me bring this down a little bit. Okay, all right, so first, okay, you can bring this down as a double bond, which means you have to bring this up as a lone pair. Okay, and then you can bring this lone pair down as a double bond and bring this double bond up as a lone pair. Okay, and then you can do the same until you reach here. Okay, now here, okay, one thing, let's go back. I want to make a note of this NO2, okay? This is condense, so whenever you see condense formula or structure, make sure you expand it, okay? This is your nitro group, and nitro group has had a history of giving students trouble. So yeah, expand out your nitro group. Make sure you know what it looks like, okay? None of the atoms have their octet rule broken, okay? So this is what nitro group looks like. And so when you're at this resonance structure, you cannot move this lone pair here and bring this pi electron down to here, okay, it would break the octet rule. See how you would have a Texas carbon here, 1, 2, 3, 4, 5. So you cannot, there's no way to bring the electrons here as like a lone pair or even as a double bond down here. So the only way it can go is up, okay? But we do end up with 3 more resonance structures, so that could be good. But let's look at the conjugate base when you pull off HA, okay? So HA, you can resonate it down and bring this pi electron up as a lone pair, and then you can do the same here. So now here, this is where it becomes important, okay? This is where it becomes important because it has reached a fork road and it has more options available for it to go. It can go to the left, and finally it can resonate up to the nitro group, up onto the oxygen, or it can go to the right and just follow the same path as this resonance mechanism, I guess, and finally put its lone pair on the final carbon. But yeah, with the key thing here is this, okay? This provides this molecule with 1 more resonance structure, though that's a point. So that's another point of stabilization. But the fact that it is able to resonate up to the nitro group, specifically up to the electronegative oxygen, see how it brought its negative charge from a carbon atom, which is not that electronegative at all,